Bismillahirrahmanirrahim. Okay, Ji, so today we'll be discussing another topic related to Unit 22 of Paper 3, Artificial Intelligence. Basically, this topic is revolving around the artificial intelligence aspect known as machine learning. So we'll try to look at the different aspects, the ins and outs of this machine learning. This will get you a basic overview of what it handles, what types of machine learning, so on and so forth. And then we'll also be discussing, we'll be looking at what neural networks do, and just an overview of what they're doing and what common applications of neural networks exist today. Moreover, we will also be looking at how neural networks can be improved for better outcome. So let's begin. What is machine learning, first of all? Machine learning can be summarized as a computer-based system that is used to perform a required task or tasks. As the tasks are performed, knowledge and experience is acquired, which result in improvement of future tasks. So there has to be an aspect of improvement. Any action that my system is taking right now should cause in the improvement of further actions in the future. Since intelligence is defined as the ability to learn from experience, therefore machine learning falls under the umbrella of artificial intelligence. Machine learning can take place in one of three ways. There is unsupervised machine learning, supervised machine learning, and finally reinforcement learning. Let's look at unsupervised learning first. The system must draw its own conclusions from its experience and results of tasks performed. It also includes analyzing and categorizing the available data. For example, consider the concept of identifying conceptual clusters. It is the process of creating clusters of unlabeled objects based on some characteristics. For example, let's say that we've entered ages that range from 10, 11, 12, then 31, 32, 33. As you can see here, there's apparently a segregation of two input values. I have values that are, say, starting from 1, and then there's another set of values that start all for 3. So right on the top, you see that there is some differentiation of these two types of data. So we can say that there are two clusters or groups of data in such a way that first cluster has values 10, 11, 12, and the other will be having 31, 32, 33. And straight away, if you look at this data, it looks different. You see that two types of data, there's two separate groups of data here, even though they're all numbers, but from their values, it can be said that there are two separate groups. Now, since we have created clusters, the next step involves creating conceptual clusters. Conceptual clusters go one step further by assigning a description for each group. So for example, the first group we created, 10, 11, 12, we can categorize this group as with a concept as young people. Same thing, we can assign another concept to the second group created as adults. So in a sense, the main difference between clusters and conceptual clusters is that first clusters just segregates data based on their, based on the data itself. If you see some sort of grouping being created, you can create groups of that data. But conceptual cluster adds descriptions to that data. So up till now, I don't know, they look different. These three values look different from these three values. And that's why apparently my computer will instantly know that these are two separate groups. But what has not been established yet, what do these two groups represent? So if I add a description to it, I am adding a concept to each of these groups, thereby creating conceptual clusters. As this is the young people and this is adults. Another example can be how we use the World Wide Web. Is recorded and stored to aid in making decisions about what products and services should be recommended to the users in the future This is also very heavily used in advertisement. So my system is basically analyzing your searches, the products that you view, and based on that data, it is making decisions in providing you with advertisements and information about products that you are probably interested in. And these products have popped up based on what you have been searching for over the internet. So this is an example of unsupervised learning in which my system is drawing on conclusions based on the tasks that are performed currently. So there has been the searching on, say, shoes, and my system has analyzed that this person, since he's interested in shoes, it is concluded that this person should be provided with advertisements that are related to shoes mostly. Now, on the other hand, let's look at supervised learning. This was unsupervised learning. Now let's try to understand supervised learning. A supervised learning system is provided with knowledge and possible outcomes and classifications of that knowledge. For example, if this is an artificial intelligence system, grading system for exam papers, it will get inputs for each paper against each paper, the answers to the questions, the number of marks that each question holds, and if you are required to mention comments for each question and their attempts, those comments will be pre-written comments will also be part of the inputs. Now, basically what happens here is that my system comes preloaded with this information. And when I provide it with an exam paper, it evaluates and produces a result based on the values that I have fed to it initially. When the system is input with marks, it returns data based on the preloaded knowledge. Another example is an expert system. For example, the medical diagnosis system that we often discuss in artificial intelligence. Basically, this medical diagnosis system is given information about the possible illnesses that often come to show under certain are possible illnesses that may be causing certain symptoms. And if you enter certain symptoms, if you feel certain symptoms, you feel a flu, body aches, and most probably you're dealing with a flu. You're dealing with some sort of a seasonal flu. But if you have very dangerous cough, shortness of breathing, then that means you're starting to move towards COVID, unfortunately. But the thing is, this information is preloaded into the expert system. This information has been catered and accumulated by a wide variety of medical experts, because your expert system is capable of handling all types of illnesses that humans, one possible medical practitioner, may not be able to do. But we have different experts for different parts of your body. We got the cardiologist, we got the neurosurgeon, we got the general physician, so on and so forth. But the expert system is supposed to be designed in such a way that it can deal with all possible illnesses. But of course, the way it's doing it is because it is preloaded with all possible information related to a wide range of illnesses. When it is input with symptoms, it simply goes through its available knowledge base and returns the possible illness that could be related to your symptoms. But the thing is, such an expert system is later tested for effectivity and based on the inputs. And whenever testing such a system, we give it some inputs, and we give it inputs for illnesses that I already know that exist. So for example, I know that certain symptoms cause a certain type of illness. I give those symptoms as an input to this expert system and evaluate the outputs. If the output is the same illness as I was expecting it, then that means this expert system is working properly. If not, then there is some sort of error. So this is how this expert system and supervised learning work. One thing to note here is that this supervised learning system is not improving on its results. It's not improving on its effectivity. It's simply returning its illness based on is returning results based on is preloaded knowledge. So there's really no aspect of its self-improvement. It's in a sense artificial intelligence, no doubt, but not in traditional sense machine learning, because machine learning transcribes that the system improves of eventual use and eventual inputs and processing. The system will eventually get better and better. But this supervised learning system doesn't necessarily get better. It's simply returning values based on what's stored in its knowledge base, and that's not how an improving system works. Improving means that it takes certain inputs, processes those results, and knows how effective the result was. If the result is effective, then it has learned a good solution. If it's not, then it will try to work out another path and try to get a more effective solution. So in a sense, it's learning and growing towards a better solution. Now, this type of machine learning is basically reinforcement learning. Now, reinforcement learning, the expert system, or the artificial intelligence system, or in a sense, which you call the agent, it learns how to best perform in an environment. It learns this. So how that happens is that basically the environment may have many defined states. The agent takes an action based on a predefined policy, which is determined by its recorded history and knowledge of the current state. The action will cause transition from current state to a new state. Each action is rewarded based on how effective it was in relation to achievement of the goal. So basically, every time I move from my current state to the next state, that next state will take me it should take me closer to my goal. Now, how close did I get to my goal is basically, meaning it should be rewarded based on the action I took. So if my current action resulted in a better progress and it resulted in me going closer to my goal, then it's rewarded better, as opposed to an action which does move me from the current state to a new state but does not necessarily move me that close to my eventual goal. That will be rewarded poorly. And my agent basically will hold the actions that it took, that for which it got a higher reward. So next time, that particular action will be considered as opposed to the low rewarding action. In a sense, my agent is learning the best possible path, the best possible action to take in a current state under certain circumstances in a certain environment. Based on this reward, the agent can decide on trying something new or not. So for example, if the reward was low, the agent will next time try to achieve a better outcome, try to achieve a better result by taking some other path, or taking some other action. And every time it's taking a new action, it will be rewarded. And if the rewards are improving, that means my agent is also coming up with more effective solutions. The goal is to maximize the reward against each action, thereby improving on the quality of policy. The process may require repeated attempts or at the same problem. So basically, you attempt the same problem, you attempt it first, you get a reward for it. You attempt it again, you get a higher reward for it. And eventually you get better and better with that same problem, resulting in better and better rewards. And at some point, you will notice that there's no further improvement in the rewards. And then hopefully you must have reached the optimal solution for it. So basically what happened is that my agent started from a very poor solution to possibly the most optimal solution. And it did it on its own by learning the effects of its action that it takes in a particular state under certain circumstances. So basically, we can see that one example of reinforcement learning could be a robot that process is doing some task. It could be, for example, painting a car, or it could be something else. It could be it could be some car that's driving on its own, for example. Now, if that robot is performing some task, it is analyzing its actions and rewarding itself based on its actions. Against each reward, it is meant to improve on that task. And eventually, it will get better and better on that task. It will get more effective on that task. And this is what reinforcement learning is basically all about. Now let's discuss regression analysis. Basically, regression analysis causes my artificial intelligence system to analyze few inputs, and based on those few inputs, it attempts to predict any further values based by trying to identify a certain trend in values. So for example, you can say here that AI can be used to predict and provide outcomes based on previously input data values. For regression analysis, the system has to be provided with input values and their associated output values. The system will attempt to investigate any correlation with the input and output values. So if I am inputting for example, in this particular graph, you can see that we have two values, IGCSE maths marks and A levels computer science marks. If these values, there is a correlation between these two values, it can be used to predict, say, for example, it is observed that a student who has achieved certain marks in IGCSE mathematics has received certain marks in computer science, A levels computer science as well. So for each maths marks, we get computer science marks. So a few sets of data are analyzed for math and computer science. And once any correlation is established between these two marks, that correlation can be used for further predicting how many marks for a particular student who has achieved a certain grade in mathematics and IGCSE may achieve in computer science A levels. But first, a correlation has to be established. The system will then attempt to investigate any correlation with the input and output values. In our case, in our example, we're talking about the input values, which is IGCSE maths, and output values, which are the relevant computer science A levels maths, or A levels computer science marks. If any correlation is found, a mathematical formula can be created, and it can be used to represent the correlation by thereby allowing the prediction of any outputs in any future inputs. So if once the correlation has been established between the IGCSE versus A levels marks, that correlation can be represented in a formula. Based on that formula, any future IGCSE maths marks can be used to predict what computer science A levels marks the student may achieve. So this is how analyzing current known values can be used, can be performed, and thereby future prediction of the values, input values from math mark, for example, can be used to create A levels computer science marks based on the previously known values. So this is what regression analysis is. So just to quickly recap, if I have a set of data, input and output values, we can, and not necessarily input values, but we can say that there has two values here that are related to each other. Say, for example, I know the results of students who have appeared in IGCSE maths and computer science A levels. I know their marks. I take the marks of, say, for example, 30 students and see that, okay, we have a trend for mathematics versus computer science marks for 30 students. When I put these values together, each student's mathematics and computer science marks together, there's a great chance that I will see some trend, some correlation between these two values. Once a trend is identified, that trend can be mapped onto a mathematical formula. Based on that mathematical formula, we can then predict any future marks. So for example, I have a student here. If I have a formula based on that previous research of 30 students, for example, or maybe even more, it's 50 students or 100 students. Now I have a student who's appearing in maths IGCSE, and he comes up to me and asks me that how much marks do you think I'll get in A levels computer science? Based on the previous data and my mathematical formula, this student who has achieved mathematics IGCSE marks, I can use his value, his current value, and predict what grade he may achieve in the future when he appears in computer science A levels. And this value that is generated for computer science A levels, even though the student has not appeared yet, but that value is generated through the regression analysis conducted on the previous values. The trend was identified, and that trend is basically used to predict what values a student may achieve for A levels computer sciences. The formula for this line, let's say, for example, in this table, the formula for this line can sensibly used to predict the future marks of A-level computer science paper from the marks scored in an IGCSE mathematics paper. So if I have an input of IGCSE marks, I can use my regression analysis method to predict what marks the student may achieve in computer sciences in the future. Now, let's talk about artificial neural networks. Basically, neural networks, revolve around, or they are based on the principle of our neurons. Our brains, the neural networks or the neurons in our brains are responsible for our intelligence. They carry our intelligence. Similarly, the neural networks in our artificial intelligence system should be able to carry out the same thing. So again, a lot of technological advancements that we see around it today, especially related to artificial intelligence, attempt to make it mimic the human body. So for example, if we have a robot who can hold things, the way it's holding it is how we are holding it. If we have a robot who is, talking or walking, it walks like us. Most probably we attempt to create, we want, our goal is to create something that looks and talks like us, thinks like us, works like us, cooks like us, so on and so forth. In a simple sense, the artificial intelligence system that we're trying to achieve right now is doing something, it's created for a time for attempting tasks at which humans are better right now. So that's what it was created for. So anyway, if you look at neural networks, networks are a type of machine learning model. This is what it looks like, or a subset of machine learning, and machine learning is a subset of artificial intelligence. So basically, you can say that neural networks is related to artificial intelligence. This is an example, a simple schematic representation of an artificial neural network. It consists of nodes. These nodes can be represented by triangles, and in certain diagrams, they are also represented in circles. But in this example, we see these nodes represented as triangles. The nodes will receive some inputs. As you can see here, it receives some inputs. And it receives inputs from one or more previous nodes. Or maybe it could be the first layer or column, and it's receiving inputs from not from a node, but directly some from other source. Anyway, it has received some input. At each node, the input is added with a weighting factor at each node. So each node with a weighting factor is added here. The weighted value is applied to a mathematical equation to compute a value for the output node. So basically what happens at each node, the inputs are added with a weighting value, weighting factor. The weighting factor is applied to a mathematical equation. Based on that mathematical equation, an output is generated. As you can see here, this node is generating two outputs here, which are further considered as inputs for other nodes. And this exact same step is carried out in other nodes as well. The weighted value is applied to mathematical equation to compute a value for an output on another node. The input values to nodes must be numerical. If they are not numerical, they must be converted into numerical value to allow for summation. So the neural network, all inputs must be numerical values because we are relying on calculations. So basically at each node, the inputs are added to a weighting factor. The weighting factor is applied to a mathematical equation, generating an output, and this output is an input for other nodes in other layers. So you can basically say that neural network is essentially a network of mathematical equations. We have mathematical equation here, 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 and there are different mathematical equations at different levels and different nodes. According to the representation on the left, the representation here, a column of nodes right here on the left receive inputs like this. The column nodes on the right, the final node, give the final output. And in between, these nodes are part of what is known as the hidden layer. So essentially, there could be many layers of nodes here, and these are all hidden layers. So where are neural networks used? If you remember that currently we're now in the in an environment where our systems are capable of looking at images and predicting what those images are. They can read text from images. They can search on the internet based on the image taken. So if you, for example, like something, you just take an image of it and your search engine will try to find where that a product can be found. So basically how that's happening. Image and video recognition, because of image recognition capabilities, we have now things like facial recognition for security and Bixby vision. So it's used here. We get images here, and based on the neural networks, it tries to predict what that image means. Then we have recommender systems. Ever wonder how Netflix is always available to recommend shows and movies that you actually like? They are most likely leveraging on neural networks to provide that experience. So based on things that you viewed before, it predicts what you will be liking next, and all recommended videos are showed according to that. Then we have audio recognition. In case you haven't noticed, OK Google and Siri have gotten tremendously better at understanding our questions and what we say. This success can be attributed to neural networks. Finally, autonomous driving. Our progression towards perfecting autonomous driving is largely due to the advancements in artificial intelligence and neural networks. Now, at each neural networks are not improved, in a simple way. Improvement of neural networks requires repeated, evaluation at each nodes. This process is known as back propagation of errors. Basically, what happens in back propagation of errors is that I start off with my column, output layer of nodes. The concept of algorithm is to adjust the weights, minimizing the error between the actual output and the predicted output. So basically, at my last rightmost column, I take each node and I give it some inputs, and I will know the result of these outputs. So this is my expected value. After giving input to this node, I will measure my output, achieved output versus my expected output. And if both values are significantly different, then I will adjust the variables in this and the adjustable factors within this node to try to bring it close to my expected value. So if my, let's say, expected value for a particular node was 9, and my achieved value is say 19 or 15, in which case I have to do some adjustment at that node. And what adjustment that is? That could be your weighting factor, and it could also be such other variations in the mathematical equations. Whatever it is, it will cause my value of 19 to come back to 9 or near 9, which I was expecting. So once we're done with that, with the nodes on this layer, we start off, we do the exact same process on the layer before that. And once I'm done with that, I will start again on a layer before that until I reach to the input layer. So this process is repeated until the output error is minimized, and we handle it layer by layer, starting off with the rightmost output layer. And anyway, if this is how back propagation of errors is found. We start off with the right nodes, the most output nodes, see what my expected versus achieved values are. I will make any adjustments in this node, considering weighting factor and equation, to try to bring my achieved values closer to my expected values. Once that is done, move on to the layers before and the layers before, and eventually reach the input layers. This is the process of, and why it's called back propagation, because you're starting off with the output nodes. Okay, anyway, with increased computing power, artificial neural networks can be created with many hidden layers. This is known as deep learning. So basically, the in-between layers, right now in this diagram, we see one, there could be 7 hidden layers, but if we are adding more and more layers, that contributes to deep learning. And obviously, in the past, it could not have been that easily achievable because processing power was limited. But now your processing power has increased, and computing power has increased, due to which I can carry out deep learning easily now. So this is your basic coverage of your machine learning topic, and this is also marks the end of our unit 22 artificial intelligence.